Welcome. Today we are featuring the roll-to-roll fabrication facility with Director Jeff Morse. The title of his talk is Scalable Fabrication of Flexible Hybrid Electronics. I am Lisa Korbieski, the Director of Communications and Marketing here at the Institute for Applied Life Sciences. We hope that with these bi-weekly seminars, you will discover what great resources that the centralized UMass Amherst core facilities offer to our campus community, the New England region, and beyond. Just a few housekeeping items. The seminar is being recorded as you just heard. All replays of the seminar in this series can be found on our website. I will put a link in the chat. We will save the Q&A till the end of the presentation. During that time, I welcome you to unmute yourself and ask your question. Next, I would like to introduce you to the Director of our core facilities, Andrew Bernard. Andrew.
Thank you, Lisa. Thanks everyone for joining us today for the third seminar of the Fall 2021 Core Seminar Series. As Lisa mentioned, my name is Andrew Bernard. I'm the Director of Centralized Cores here at UMass Amherst. If you've joined us before, you've heard me discuss our state-of-the-art labs, instrumentation, equipment, and world-class experts who are helping researchers at UMass and beyond drive discovery and pursue scientific endeavors across all disciplines. Of course, here are open to anyone from students through senior scientists, regardless of your affiliation, including researchers from other academic institutions and commercial operations. In order for these operations to maintain affordable and for the course to receive the investment it gets from the university, we are reliant on publication acknowledgements and acknowledgement of the work you do with us. This is important for us to be able to show value to the senior leadership who continue to give us financial support. And also for our core staff and faculty who may not have their own independent research, this helps them grow their own professional development. You can learn more about suggested authorship guidelines on our websites, and I'll put a link in the chat in a little bit. Also want to mention for those who have not worked with us before, that there are opportunities to engage and receive funding to access the cores, including IELTS investigators who have access to core credits and funding through the centers. And for those external to UMass, there's the Mass Innovation Voucher Program that subsidizes companies in Massachusetts at up to 75%. If you have interest in any of these programs or working with cores, you are welcome to reach out to me or any of the core directors, and I'm always happy to put you in touch. With that, I'll turn it over to Jeff Morse, Director of the roll-to-roll facility, who will discuss capabilities and resources available to our research community. Go ahead, Jeff.
Good afternoon. So, as mentioned, I'm Jeff Morse. I'm the Director of the Advanced Print and Roll-to-Roll core facility at UMass Amherst. Changed on me. Here we go. Okay. Sorry about that. Something happened to my screen. Am I still on with you guys?
Yeah, we can still hear you, Jeff.
We can hear you, Jeff. We just can't see the slides, right?
Yeah, let me go back to share screen. So suddenly it went, okay, what's it doing? Sorry about this. Here we go. Let's do this again. Okay, all set. Okay. So I'm Jeff Morse. I'm Director of the Advanced Print and Roll-to-Roll core facility. Today I'm going to talk about several aspects of the roll-to-roll core facility, what it is, how it functions, and what our capabilities are. And then I'm going to go into some of the work that's being done or has been done in the past as some examples, both projects and application spaces. So basically, the core facility is an open access user facility. It's accessible to UMass students and researchers, other academic institutions, as well as industry users. Our capabilities are extremely comprehensive in the print and roll-to-roll area and include coatings, printing and patterning of various types, and I'll explain some of that. We have a host of analytic capabilities to further assess the results of what you're doing. That can be surface analysis, that can be profilometry, both imaging and linear profilometry, just to measure kind of thicknesses and patterns that you're fabricating, that you're making. And other aspects, electrochemical testing, surface rheology, and surface energy analysis. So different things that help you both with understanding of the materials that you're working with, of the surfaces you're working with, and other aspects of how you can better fabricate your devices and or scale them towards some application of interest. We also work in areas of materials. We work with formulations, we work with composites, and we also do a lot of work with standard industrial inks, metals, and dielectrics. Many times we're working with our collaborators, whether they are faculty research groups on campus or other industry partners who really want to assess different types of options from a material standpoint, maybe something they're developing, maybe a new ink or something that's been around industry for a while that might be suited for their application needs. So basically, I'm just going to cover some of the tools and technologies that we have in our facility. So on the left side here, we just go through a handful of the tools. I'm going to get more in depth on the next couple of slides. So basically, we have a series of customized roll-to-roll test frames and printing coating tools that have been fabricated and designed for us. We also have some standard kind of off-the-shelf commercial machines and pieces of equipment. So for example, here we've got microgravure, slot die and flexographic coatings. We have a roll-to-roll spatial ALD that's being designed and built specially for us. We have inkjet and photonic cure. I'll explain a little bit more about what that is. We do have a continuous pick and place tool. So that's for automated assembly of silicon devices and surface mount components on printed flexible substrates that we are designing and fabricating within the facility. We have roll-to-roll nano imprint lithography, which is an emerging technology to form patterns down in the sub-micron and nanoscale on surfaces. And we have other contact and direct write lithography and mass lithography capabilities. Some of the applications really leverage some of the advanced material systems and devices that have been developed at University of Massachusetts and elsewhere, but mostly a lot of the focus coming out of the Polymer Science Department, the Watkins Group, and several other groups, both in chemical engineering and polymer science, have been contributing both materials and process aspects to the facility. So for example, on the right, we have some examples of direct printing of metal oxides and metals using nano imprint lithography. We have flexible hybrid device integration where we are printing a variety of conductors on flexible substrates using different techniques. And then we might design that into specific circuits and integrate that with specific components, whether that's silicon or packaged devices and systems. We've done some work in printed microfluidics and biosensors. We continue to do a good amount of work in printed batteries and micro battery systems. And we've also had some work in structural functional surfaces. So these are actually interesting applications where we can provide not only a material on the surface and coating, but we can impart a pattern into that specific coating to give us something like structural color, a specific photonic and optical applications or optical properties that we can get onto that surface for some of these emerging applications that we're seeing. So if we look beyond kind of the research and science, we've got several pieces of equipment that are more lending towards scale up and commercialization. So on the left here, we have some examples of in-house piece of equipment that we have procured. The top one is the Frontier Coaters. That's basically a workhorse coating system that we use. We have numerous industry partners as well as some of our academic collaborators that are utilizing this piece of equipment. All of our web-based tools are 6-inch wide substrates and rolls that we work with. And this one in particular has pretty extensive exhaust systems. So we can look at resins and coatings that are more solvent-based. We can look at basically using the extended drying ovens, multi-state drying ovens. We can look at kind of the relationship between coating thickness, web speed, and drying temperature to optimize the process for the customer. The next tool down is a rotary screen print, which we have put in one of our lines as well. So again, the same thing. We're looking at high speed, high throughput printing of different materials, whether they are conductors, battery electrodes, and optical types of resins and components that can be either thermally or UV cured. And we've had numerous projects with industry, both as well as some of our academic research groups looking at this. And then the bottom one is our Northfield slitter and laminator. Again, that allows us to work with substrates in terms of defining the width of the substrate if we get rolls that don't meet the requirements of our tools. And we can also do lamination and or bringing together multiple substrates into one common, I think this is a thermal assembly approach that can allow us to do that. On the right here, we have a more comprehensive list of the different tools we have. That includes roll-to-roll sputter deposition and roll-to-roll deep reactive ion etching and ion beam milling. These are vacuum-based systems, so we have a variety of gases and target materials that we can utilize in those. As mentioned, we do have roll-to-roll spatial ALD on our list, atomic layer deposition. So we anticipate that coming in the next 6 to 12 months, we believe. As mentioned, the Frontier coater, again, allows us to gravure or slot die coating with controlled emissions and exhaust. The difference between those two types of coatings depends on the thickness and viscosity of the resin or solution that we are coating, as well as what the final kind of shrinkage of that coating as we cure it. And so that will depend on which one we use there. We also have roll-to-roll inkjet gravure, rotary screen printing. That line has what we call a pulse forge. It's a xenon pulse flash lamp, as well as infrared cure. And what those allow us to do is get further, what's the right word, sintering or curing of the material we're putting down. For example, if it's a silver ink, you want to sinter that to get the best conductivity. Other researchers are looking at taking polymers and polymer composites and further sintering those to form basically carbon composites or graphitic composites. So it's very interesting what some of the research directions may be going with some of these tools. We additionally have roll-to-roll contact lithography. And so that's basically the analogy of photolithography, where you're taking a UV source, you're taking a photomask, and you are imparting a pattern into a photoresist using that optical source. In this case, we do have some alignment capability with that, and we are targeting achieving less than 5 microns of alignment and registration resolution. Nanoimprint lithography, excuse the spelling on this, that's a similar approach, but what we do is we make a 3-dimensional mold. We wrap that around a drum, and as the roll coated with a specific resin passes by that, it imparts that pattern from the mold into the resin that's coated onto the web-based material. And so that way we can achieve patterns that are down to sub-micron, nominally around 100 nanometers or so is possible, possibly even better, smaller than that on a moving web roll-to-roll platform. And so that's impressive work, and we're finding now emerging applications and interest in that technology. So that was ahead of its time when we ordered that piece of equipment. We also do sheet base and roll-to-roll pick and place for automated die attach. Secondary processes include a host of substrate preparation and materials preparation, as mentioned with the slitter laminator, optomic aerosol printing system, inkjet and photonic cure, wafer-based nanoimprint lithography tool, and a flatbed screen printer HMI tool, where we can actually just do probably about 6-inch square sheets imparted with a pattern, probably sub 50 micron type of pattern resolution in different inks. We've done this in carbon and silver inks, etc. The labs include a host of other ancillary capabilities for analysis. We got a dry room for battery research. We have glove boxes for controlled environment work, where you want to eliminate air, oxygen, and water vapor that may impact your materials work. So there's definitely a lot of different activities, a lot of different capability within these labs. Just going to show you images of some of these systems as we go here, so you get a sense of that. So upper left here is a Trion reactive ion etch. That's a vacuum chamber. We actually load the full roll inside that chamber and then complete the process. And we can just do short runs of a few feet or something, or we can do full up to about 500 feet if that's what the customer wants. On the right is our AJA sputter system. Same thing. The bottom image below that on the right shows the chamber open. So basically you have the whole roll media holding the web, and then that basically goes around the chamber where we have up to 4 different metal or dielectric targets inside. And we can also pre-clean the substrate, coat the material on it to enhance adhesion and uniformity, and do all that inside the chamber once pumped down. And again, we can just do a few feet, or we can do up to about 500 feet or so in a continuous run. Bottom left is the prototype of the roll-to-roll atomic layer deposition tool. And to the right of that on the bottom is the custom head that was designed by our partner Carpe Diem that gives us numerous reactant gases. And again, this is kind of a higher quality material deposition system that can do this at pretty low temperatures. So it's atmospheric base or inert environment base, but it can deposit these films at fairly low temperatures. So you don't need real high temperatures, and you can do those on even some of the plastic substrates that are out there. Additional emerging capability, as mentioned in the top right, we have this coating capability with the photonic cure system in the middle, the pulse forge, you can see that. And basically that's a UV flash lamp, which basically just hits the substrate with these intense UV pulses that heats up the films that have been patterned and coated on that, and then cures and densifies those, basically sintering them. The benefit of that is you can actually cure silver and other inks at much higher temperatures than the substrate can withstand. So that's a benefit to getting better and better performing conductors, for example, as a means to get the circuit design that you require and the performance that you require. Below that on the bottom left is the aerosol jet Optimex system. So again, that is basically a atomizer where you take an ink of varying properties, you put that in these atomizers, it basically aerosolizes that, and then it shoots it out a jet nozzle, and you can, in an automated design fashion, spray that basically over the substrate in the pattern that you want, that you desire. So that's now up and running, and we've been doing a lot of work with that particular system lately, both with silver ink materials and carbon ink materials. So there's a lot of interest in that. Top right is the Bessey Evo 2200. So that is a automated pick and place tool. This is kind of an industry standard tool that's used within the semiconductor and packaging industry. We have adapted that to be roll fed. So you can actually have a pre-patterned substrate unwind. Basically it indexes about 12 inches at a time. And then the system, the tool itself will populate that with either surface mount components or silicon devices. And so it gets pretty good feature resolution, I believe, plus or minus 7 microns. So you can come in with some pretty sophisticated silicon chips and pattern and assemble them, align and assemble them onto your substrate with good reliability. Below right is the HMI flatbed screen printer. So again, the same thing, you might use this to make sheets of your pattern conductors or some other pattern you're looking for, and possibly material. And so again, this will do the patterning in a screen fashion, and then allow you to do multiple sheets in a row or whatever you desire. So just some examples of some of the emerging equipment. In addition to cutting edge side of things, so not only is the nano imprint lithography fairly cutting edge, but we've also got a contact lithography. So again, this will coat a photoresist and pre-bake it. It will then align that to a photomask, which is wrapped around a drum with a UV exposure source inside it. And then as it rolls past that, you get a pattern formed in the resist where the UV light is allowed through. Basically, this allows us to then create these patterns, and you might do something subsequently like either an etch or a deposition to create a metal pattern or some other pattern on that substrate. Ideally, what we would do then is we'd come back through and align another pattern over that. And so that's the advantage of this. If you look at the image on the right, kind of shows our drum. In the center of that, you can see a little bit of a purple color where the UV source is coming out a little bit. Also, the picture below that shows kind of the blue image. But if you look at that top right picture, you also see there are 2 cameras that will image the alignment capability. So basically what that does is allows us to adjust in an XY translation the position of the substrate with respect to the photomask, so you can hone in on the alignment between the existing pattern and what you're trying to pattern. So that's something we've been doing a little bit of work with, but haven't fully vetted that out. But again, we're targeting something that is less than 20 microns, possibly down to less than 5 microns in alignment resolution and accuracy. So, okay, so just an example of the range of partners, both industry and academic, that we have, and this doesn't include people who we've already done a great job for and have moved on and scaled up to more commercialization, as well as many in the pipeline right now. But basically, we've got a series of mostly small companies. A lot of them are taking advantage of the Massachusetts voucher program to get some subsidy to work in the core facility. But as you can see, we're kind of across the whole range of energy. A lot of that's in the battery component technology, filtration, so still energy environment, a couple more in the healthcare and kind of protection, antimicrobial mass and wearable biosensors. Assessments for conductive materials. We're getting a couple partners now in having us do pretty broad studies on their specific materials. These are Massachusetts companies. They've been around for a while, and now they're basically developing next level technologies and products and having us do the assessments for them and comparing that to other competitors out there. So that's some nice work we've been involved in lately. Again, more battery companies, a couple defense, small business, SBIR type of contracts. Recent project with a company called Imagine, where they wanted us to fabricate MicroLens arrays using nano imprint lithography. That's for displays and augmented reality, virtual reality type of applications. And then we've had an ongoing relationship with the NextFlex manufacturing consortium for flexible hybrid electronics. So we just recently finished a case study in ultra-thin silicon die handling and assembly, and that's for general flexible electronics applications. Academic-wise, we've had partnerships and collaborations with Northeastern University and Penn State University under NSF funds to look at different aspects of manufacturing, active registration and alignment, as well as nano imprint patterning for structural color for the Penn State folks. We have an ongoing project starting up with the Watkins group at UMass Amherst, where we're looking at coatings and nano imprint lithography for multifunctional structures for DoD applications. Overall, we've got multiple UMass faculty research groups utilizing both our analytical, electrical test, and other printing capabilities. And some of those are larger projects and more extended, and there's some are just used as necessary. So there's different ways that the groups are interacting with us, and we welcome basically any needs and ways that you do want to work with us, and we'll offer up assistance in whatever your application needs are. So I wanted to step back a little bit now and provide some examples of some of the development projects that we've been working on in wearable health monitoring systems. So a lot of this was originally funded going back, gosh, almost 5 years at this point, by the NextFlex Consortia Manufacturing Institute. And a lot of that was just looking at selecting a wearable device application. So for example, on the left here, we show something that might be a fairly advanced platform where you might have sensors for monitoring ECG or pulse oximetry, and eventually other types of body function capability to get an assessment of your cognitive and physical health status. So that's the goal primarily of the military, but this overlaps kind of the general kind of athlete, weekend warrior, and certainly in the healthcare spectra, where many of these can be monitored for patients, for example, and just good to know this data and record this. So there are platforms out there, but nothing that's very low cost and very wearable and possibly even disposable. Those are some of the future visions on how these products may be kind of established and developed to be worn and utilized. So for example, we have sufficient electronics in here, microcontroller, A to D, and sensor interfaces, even wireless Bluetooth, for example, to transmit data externally. We would integrate those with printed conductors, printed circuits over a flexible substrate of some sort. And then they would attach to the specific sensors that are interfacing the skin and the body at some location. If we look to the right here, I just give some examples of some of the focus of the work is basically you're printing and patterning of conductors, whether that's electroplated copper on flexible Kapton. That's been the industry standard for years. It's not made through an additive process. It's generally an expensive subtractive process, and it's basically embedded in the supply chain in all of the packaging that we see right now for silicon systems and so on that are in most of the products we use, computers, phones, etc. What these applications want is something that's not only lower cost, but even a more flexible alternative types of conductors, inks versus copper plated, and less rigid applications. So many of these are just born out of the silicon IC packaging, but now this is kind of emerging into a new market area slowly but surely, and we'll have different parameters, different levels of performance and requirements, and eventually different cost models. In part, we've also looked at thin silicon ICs for flexible printed circuits and use some of the capability in the facility that we have there. And eventually, many of these applications, the customer wants us to look at the scalable roll-to-roll patterning of the conductors and eventually integration of all the system components. So just in general, what we're doing here is if I show a schematic and a example board on the left of the three images. So these are the rigid printed circuit boards that we see today. They are using packaged ball grid array chips that are basically soldered onto these boards. That's a whole industry that's hard to disrupt. And so basically we're looking to transition the specific designs to now something that's completely printed and completely flexible. And so that's the objective here. And we're looking at what are the new emerging methods that'll give us both the cost and the actual performance, electronic performance of these systems, and allow them to be worn or implemented in new ways, conformal locations and structures, body worn, etc. And so we start here by taking these designs, which come both in schematic and circuit diagram layouts, and we work with programs that we have available to us where we can convert them now to a specific layout on a flexible circuit, and that is going to employ the design rules for either single or multiple layer printed architecture. So that's kind of one of the beginning points for us. Now, the critical thing, which I'm going to talk about from here on, is how do we determine what those design rules are? In other words, how small of features can you print? How close a packing can each of your lines have? And how do you deal with 2- and 3-dimensional types of architectures? In other words, front and backside printing, feed-throughs, and also crossovers, where you have one conductor crossing over another without shorting out to that. So those are critical process capabilities and steps that you want to see in your printed electronics. And so I'm going to talk a little bit about how we achieve that. So basically, some of the workhorse capabilities that we have in the roll-to-roll facility are the inkjet and aerosol jet patterning of printed ink. So silver's been the workhorse that most people use. We've had some of the students and research groups look at both carbons and copper, for example, which you can get in ink form. But regardless, both of these techniques are digital. So you put it in a design, you load it on the computer, and then it'll print that out. Basically, you're working now with the substrate and the specific ink properties to optimize that pattern so it doesn't bleed out and be larger than you want, as well as it doesn't bubble up and form something that just won't adhere or stick to the substrate. And so that's where we work with both for the materials, the surface energy of the substrate, whether it's Kapton or PET, which is another form of clear plastic. And then we work with post processes, the curing temperatures, and then eventually the photonic sintering, which can further densify and improve the line resistance of these printed conductors. And so I show that tool on the bottom right. We have both that in as well as the center here, the PulseForge 1300. That's basically a standalone unit, not roll to roll. And then we do have the same thing, roll to roll. Other methods to form the printed circuits are screen print. So we spent a lot of time looking at that. The advantage of screen print is overall you can put down a thicker ink. And so what we show here, both in the bottom table as well as the graph on the right, is you can print these patterns and you can get much lower resistivities for the same line width. And that's because you're getting probably anywhere from 5 to 10 times improvement in the overall thickness while being able to achieve as good or better line width patterning performance. So the images on the top left show 4 different examples of different line widths and patterns. You can see we get very nice sharp edges, very crisp, very clean, and you can get patterns down to 20, 10 microns types of features. Very typically 50 microns is very doable and reproducible, but you really have to work at it to get that optimal. But we do show some pretty sophisticated patterns here. And if we compare resistance and line resistance here, we're seeing that, yeah, we're getting definitely factors anywhere from beyond 10 and so on. And that's because the inkjet also is very limited in thickness. A lot of times you're only getting about a couple tenths of a micron in thickness, and a micron is really where it tops out. With the screen printed, you're starting at about 1 to 2 microns, and you can get up to, I think we've demonstrated about 6 to 8 microns, and certainly if you're doing it right, you can get up towards 25 microns, depending on ink viscosity, surface parameters of the substrate, as well as other aspects of the printing screen and so on. So there are some benefits to that, but again, there's always something you have to watch out for or misinterpret as you look for these benefits. So we see everybody has different requirements of what they're looking for. And I think in part, this is why we see so many different print capabilities still out there being investigated, being used. A lot of this goes back to newspaper printing. Massachusetts in the Northeast has got a history of roll to roll and mills and stuff where we are creating paper, we are creating print with inks. We've got the Polaroid and Kodak technologies that were more or less located in the Northeast. And a lot of that was more for coatings, but a lot of that now is transformed into printing. So this is some example of flexographic printing. So it's a little bit different in that you basically take a stamp, you wet that with an ink using another technique or a rod, which basically picks that ink up out of a well. It wets that pattern that you have on a stamp, and then the stamp just puts it down on your substrate. Again, that's how newspapers were originally printed. Now we're looking at silver inks and other ink materials. If we look at the images on the lower left, that's basically a flexographic head that's now been implemented on one of our roll-to-roll lines. And basically, we just took a stamp that we had fabricated. We put that around an existing kind of a custom roll setup that we assembled, and then showed that we could pattern that down on both Kapton and PE substrates with pretty good fidelity. So again, I'm showing the same circuit patterns that we showed previously on some of the screen print and inkjet work. And again, we got some line spacings here that are pushing down to sub 30 microns. So we got pretty good fidelity, had to be very careful about the speed of the process and other parameters on both the substrate and the ink, but we were able to reproduce pretty good fidelity patterns. I think in the upper right, if you look at the middle pattern, those are some test features that we had printed. And you can see you're getting down to 30, 20, even 10 microns. It's getting a little thin there, but you're able to get those types of features in such a printing technique. So again, it gives us different tools and different weapons we can use when we're trying to print really challenging line widths, as well as achieving a reasonable line conductivity or line resistivity. And so those are all parts of the challenges that we face when we're talking to potential users and customers about what their needs are, what they'd like to do. Not everybody's so critical, but when you're building basically a more complex circuit, you want to have these options in hand so that you can get at least the parameters for a more densely packed circuit that are going to be closer to what you need in the end, especially when you're going to start integrating silicon and other types of components with that. So finally, in terms of the patterning approach, we did some work both with photolith patterning and electroplating, and this is more for high density copper circuits. And so typically on this, we're using Kapton substrates. We can use PET, there's no reason for that. It's a low temperature process. Basically, we expose a photoresist pattern with a photomask. We develop that. And in this case, we had a copper seed layer already coated on the substrate. For the exposed areas, we go into an electroplating bath, and then that will basically plate up or electrodeposit films as a function of time and current and so on. And what we've been able to achieve, if we look at the right, is pretty good patterns. I mean, the pattern limitation here is dictated by the photoresist pattern, which technically you can get down to 10 microns or better. It's submicron for silicon photolith patterning, but in this case, the resolution is limited by a flexible plastic mask that can be created. And those are typically on the order of 10 to 20 microns. In many cases, they're going to tell you 50 microns is a design rule limit, but we've seen a little bit better than that. And when we electroplate, it just follows whatever pattern you created in a resist. We get very nice, crisp patterns. In this case, we have, I think, line and spacing on the order of 60 microns line width, 30 micron spacings. We've plated copper thicknesses up to in excess of 10 microns, and you could go further if you had a thick resist. And if we look on the upper right, we show a more complex integrated circuit, all copper, good adhesion on Kapton, and we've assembled devices and components onto this. So it actually is a much better approach if you need high current handling capability, low line resistance. This is going to be in the milliohms, possibly even lower, because it's copper, as compared to a silver ink, for example. And in the lower right here, we just show a imaging profilometer measurement of an example thickness of a line, again, on the order of about 11 microns in this case, and pretty good crisp line with pretty smooth surface. And so that's another thing, is that a lot of times these silver inks have very rough surfaces, which could impact attachment of silicon die or other integration. If you're trying to make crossovers, you might have to have thicker dielectrics that are going to insulate between a couple of layers. So there's other issues that need to be considered when choosing which process flow you want to follow, particularly in patterning, and even more critical as you're going to higher density printed circuits. So what have we done with these types of things? This is an example of some of our first sensor design and integration. We use both flexographic and other printed substrates, circuits on the flexible substrates. And then we integrate first manually with surface mount components and headers to attach external leads to our electronics. And this just shows an example of a 2-electrode ECG circuit. And in this case, we just soldered lines to the standard off-the-shelf ECG electrodes and got test results shown here in the middle of an ECG signature. And this is actually a real signature off of a person. On the right, what we're showing is where we go to next generation. So basically, we now are integrating low energy Bluetooth system on a chip and signal processing components, so that we can do some intermediate processing of the acquired data. We can then digitize that and then transmit that via Bluetooth to an external handheld where we can further look at and record the data. So some examples of other technology integration that we did on the way was looking at the automated die assembly. And in this case, we were tasked to look at ultra-thin silicon die. So the interest in ultra-thin silicon die is several-fold. One is the profile of these wearables. If you look at typical printed circuit boards, or even printed circuit boards now that are migrating to flex, you still have a lot of components that are fairly thick. They're much thicker than the substrates themselves, and they still stick up a lot, and you still need to encapsulate them if there's any type of environment where they might be impacted or further abrasion on something, and so on. And so basically there's an interest to thin the silicon die, forego the packaging, and directly assemble this and put it using a conductive adhesive onto the flexible substrate. The other advantage here is if you get thin enough, and that's believed to be around 30 microns, is the actual silicon die becomes flexible. So as you bend this substrate, if you need some conformal type of application, you are not going to further stress that device and further impact or damage the conductive leads or the attachment. So that electrode interface could be critically impacted if this starts to bend. And so we did both a lot of assemblies and handling with the ultra thin silicon die. In this case, they were about 45 microns. And the problem there was just handling them at that thickness is you break a lot, you have other stresses and so on. And so we both worked through the handling method, as well as got some very good components now with the Bessie tool, where you can very carefully eject these off of a wafer tape. So after they're diced, you're able to eject them, pick them up with a vacuum, and then position them and assemble them with a conductive, one-dimensional conductive adhesive, so that you can get good alignment and good conductivity of all electrodes on the lead. So in the bottom right, we show an example of one where we have placed that onto a test circuit. And I think the upper left, so we first have one on this test array that we've used. And again, these are, I think, line spacing, line width of about 60 microns, spacing of about 30 microns, where the critical pads are on the silicon. And on the right, we show kind of an angular image where you can see how thin that particular silicon die is. Lower right is just a top-down image of that. So you're seeing that the adhesive is now just pushing out beyond all edges. And so that's just the right amount. Problem is, if you get too little, you don't get good attachment of all the leads. And if you get too much, it comes up on the top and starts to impact your vacuum pick tool. So those are all issues that we had to work through, understand, and develop methods to improve those. Bob Stevens in our facility has probably done the most work on this, and is kind of the guru. And then others have come in and helped with that system. Bottom left, we just show a full array. And we've done, I think, up to 96 die at a time over a full sheet, and have been able to just go and continuously pick and place those with pretty good yield. And so that's impressive. And we can just work with regular thickness chips as well. It's not as big of a deal. And this just, again, shows kind of both the Bessie automated pick and place tool. The center is kind of the inside of it with the images and all the sophisticated machinery. And the right is just an example of a flexo printed circuit, which we had on a continuous web. So we loaded that on, and just in a simple demonstration mode, showed that we could just continually pick and assemble single individual silicon components onto something as it was moving along. And again, this unwinds, and it'll index to a certain point, stop. The piece of equipment will populate that region, and then will index to the next area. And I believe that's about 12 to 18 inches in length each time. So now stepping back a little bit, so now we want to go to more sophisticated printed electronics, again, before we attach the silicon devices. And in many cases, I believe if you look at the circuits here in the middle, both top and bottom, you see kind of some headers, which are the dark, the black plastic component on the top with leads that come in. We've got a yellow component, and then we've got a series of surface mount components in there. Now, what we wanted to do was have something where we could print the crossovers. What we've done previously is we just have pads that come up to a crossover area, and then we take a surface mount component. We call it a 0 ohm resistor. So it's basically just a bridge that we create over that, but we have to hand assemble that. So that's no way to do it. So this is some work we did with our partners, United Technologies, and again, showed that we can screen print. The green here, if you look at the images on the left, the green is a dielectric. So we can actually align and print that over the conductor. And then we come in with a second conductor and we print over that bridge. And so now you're connecting two pads in the opposing or orthogonal direction without shorting to the lead that you're crossing over. And so that allows us to go to 2 dimensions in our layout and further can enhance the density of the circuit design. And so these are what I talked about as far as design rules. Once you can start going to crossovers and then possibly vias that go through to another printed circuit pattern on the opposing side of the substrate, now you can start to compact these, get more sophisticated circuits and printed circuits, and look at even more complex systems. And all of these are basically systems. You have sensors, you have analog data acquisition components, you have computational components, and you have some type of a data transmission, wireless transmission component. So they can get pretty sophisticated very quickly. And the problem is you need to integrate matching and other surface mount components with this system along the way. And so what we found is that we can handle many of those elements using the automated pick and place tool and further enhance kind of the ability to fabricate and assemble these without a lot of manual effort. So this is an actual ECG circuit printed, and we've got some data here. The top red curve is actually somebody wearing this, and the signal is not quite as good. The bottom curve is a heartbeat emulator that we have on campus. I believe it's Professor No, who's both within the nursing school and the ECE department. And so basically what we can see is on body, you get a lot more artifacts, noise artifacts, whether it's motion, breathing, signal integrity is still okay, but not medical level quality where you can actually look at the waveform of the heartbeat. But we can get there. I think further sophisticated electronics and improvements in overall design may help that signal to noise level. Here's some examples of how we actually develop materials and designs to specifically integrate the electrodes. And so this is an example of a topside printed circuit made of silver, like I've just shown you several examples. On the backside here, we integrate carbon electrode, this specific material that one of the Watkins postdocs was looking at. We're able to pattern that, put that in the electrode, print electrode configuration, and then wear that, do some example testing in a body worn situation. And the same thing, when they're actually very still, they can get good data. Once you see some motion, you start to get artifacts and the signal integrity gets a lot worse. So it's just under normal conditions, probably still needs some design improvements to further make that high quality data. And similarly, we've looked at pulse oximetry. Again, spelling is not so great here, but we'll bypass that part. Again, this is an LED array of 2 different colors. So these are basically the same thing that you wear on your finger when you go into the doctor's office or the hospital. They want to measure your blood oxygen. 2 wavelength LEDs. A couple in our group, both in the Watkins group and Bob Stevens, kind of printed these out with both inkjet and screen print, different options, integrated these LED modules onto them, and then showed that you can actually get data directly out of these. We have designed more sophisticated printed circuits to accommodate these and handle these. And so these are system on a chips with LED modules integrated and eventually Bluetooth type of data transmission. So I'm going to go through a couple projects real quickly because we are running a little short on time, but I just wanted to go through some other examples of things that we've been working on. So this is a project using a MicroLens array for printed photonics. Again, this is more working in the nanofab and microfab facilities here on campus, creating a nano imprint lithography mold. And so this is a specific design where we wanted to create an array of lenses having specific geometries. So these are about half micron pitch. And ultimately they wanted an array on the order of a centimeter square, which is pretty much state of the art, getting those types of features over that area. we got up to about 5 millimeters by 5 millimeters. We used specific processes to etch these patterns, forming a master mold from which we created a daughter mold. And then we're able to stamp these patterns into a resin having a specific dielectric constant or reactive index of refraction, so that they could get the particular photonic and optical properties that they were looking for. So this is just an example where we pattern these using e-beam lithography. We etch these in silicon using reactive ion etching. And then on the lower right that we created a PDMS daughter mold from that, which eventually is our stamp to create these patterns in the refractive index material of interest. Now we took that PDMS mold and we stamped that using the NanoNex nanoimprint lithography tool into this resin coated on a silicon substrate. You can see the silicon master mold on the upper left. Below that is the replicated PDMS stamp. A little difficult to see, but basically it's an array of the same thing, just opposing pattern. And then on the lower right, we show examples of these patterns now stamped on this resin that's coated onto a silicon substrate. The lower right shows an example of an array of LED OLED devices supplied by the company over a wafer, and we're able to then stamp those arrays into that particular device. And so just an example of how we take different things, doesn't always have to be roll to roll. And I'm just going to quickly go through some of the, most of these are out of the Watkins Research Group early on in the facility as we were coming up. So basically integrated sweat patches using printed microfluidics, printed sensors where we use inkjet patterning techniques, integrated those with the microfluidic devices, both in a closing valve and a sensor architecture. We're able to do that level of integration. So this is mostly student research. And then again, same thing, creating sophisticated electrode structures, giving high surface area for glucose sensing and cortisol sensing, and different either resistive current-based sensing technology or electrochemical sensing technology. So again, a lot of this starts with printing and fabricating patterns of conductors with inkjet or microfabrication techniques, and then goes to integrate those with more sophisticated systems, in this case, microfluidic-based architectures. And then finally, broader studies on how those microfluidic architectures perform. Again, printing and patterning these with inkjet, with nanoimprint lithography, and other methods that could ultimately be scalable via roll-to-roll. So finally, I just want to wrap up giving a quick overview on how to work with the roll-to-roll core facility. So we've got a set of professional staff now, and we are certainly adding more, both in the technician and engineer level in the labs, in the core facilities. Barbara Stewart is a roll-to-roll lab manager, great range of industry expertise in coatings, materials, process development. Bob Stevens, expertise in electronic design, packaging, process development. He's been running a lot of the Bessie tool, the automated pick and place, and along with Barbara has been running some of the new inks coming through the inkjet printer, and has also gotten the aerosol jet Optimec printer up and running. Neil Maida is the device fabrication nanofab lab manager, has just rejoined us after originally working in roll-to-roll several years ago, as he came in with our partner Carpe Diem. And so he's working on a lot of process development and equipment aspects, as well as brings his expertise back into the roll-to-roll facility on occasion. Sandre Branso is our contract with Carpe Diem, and is also process development and maintenance in roll-to-roll, and really brings in a lot of that core roll-to-roll capability that, combined with Barbara, just give us really a great a starting point in working with industry partners and the faculty research groups. So how to work with us: we can collaborate on grants and proposals, we can be co-investigators, and or we can just provide facility access at the nominal published rates for specific tools and processes. Student users, we provide assistance on major tools, training for all the other tools and labs, And so most of the students are coming in working on their own, and we're there to help as much as we can and learn from each other. It's a two-way street on that. Industry partners, we're working with a range of industry partners on roll-to-roll and broader projects, both at academic and industry rates, depending on the circumstances. And we can both partner and co-PI on proposals or sponsored R&D. So a lot of ways people can work with us. Me, I got a background in engineering and a whole range of interests technically, but more recently it's in the print electronics and combining a lot of my prior history technically with what you can do now in print electronics and systems. So finally, thank you for the time and listening. Really the best thing you can do is reach out to me. You can reach out to Andrew if there's interest in learning more. Also, I direct you to the website at the bottom here. You can actually find more detailed information on specific pieces of equipment. You can also get a rundown of the rates and how to best work with us and what that might cost. And then certainly reach out with specific questions, or if there's just general interest. Certainly we like to hear what your thoughts are, what you're interested in, and how we can best help you and work with you. So with that, I'd like to end this discussion and I guess open up to if there are any questions.
Jeff, I do have one question.
Go ahead.
You were talking a little bit about the industrial partners. Have any of the industrial partners looked at the roll-to-roll facility as a long-term partnership with their products?
So we've seen a couple, which again, the long-term nature is still to be determined. But you know, more recently, we have a startup company which is moving into the collaboratory, and we'll be using specific elements of the facility, and then they will transition to scalable manufacturing. So we anticipate they'll work through their process for their technology, and then they'll scale it up on roll-to-roll. And so that might be a 2-year type of partnership. And then we've also had other partnerships which are just coming for periodic use. And we've had some that are already pushing like 3 years. But it's not an extensive amount of use. I think we do our job well, which is the goal here. But that benefits the user and doesn't keep them in the facility. And then we have other people that are intermediate. So you know, we have example projects where, you know, they are starting to go be prolonged, and that's because their challenges are both significant in terms of what they're trying to achieve, as well as a little bit of a moving target. So that's where if the products aren't clearly defined and the process flow isn't clearly defined, those things can kind of continue on. And so we see them at all levels right now. And, you know, we think the long-term partnerships are going to be best for everybody involved. And like I said, we've had multiple projects that come in. The companies do their homework, we do our homework, and we get them out the door very quickly because we're very efficient at doing what we do. And the best example is one company, Zwitterco, where they launched a product and then they're back to develop the next one. So with some changes in what they're trying to achieve. And so that's the success that we want to impart, particularly to Massachusetts-based companies. And then also find ways where we can get these longer term types of interactions. And that's where some of these proposals, SBIR projects, they're coming in a little bit more like that, where we're looking to solve and be part of a proposal and solve a bigger problem for the partner.
Okay. Thank you.
Hi, this is Dave Follett. I had a question maybe on the opposite end of the spectrum. I think when I look at the things you're doing, it looks like it's sort of a big project. There's a lot to set up to do these things. And sometimes, you know, we'll give tours and there are people who are maybe just doing tiny things? I mean, what's kind of the smallest level engagement you could have with roll-to-roll?
So, and I'll couch this from the standpoint of both industry and academic users. So the smallest engagement is you're just coming in to use like our surface profilometer and or another tool, even inkjet printers. Some people come in, do their printing, they more or less get trained and work on their own, and they're in and out quickly and on their own. A lot of what I showed on all of that printing was for one big, that was a 2-year project, pretty well funded. And what that did was get us up to speed. And you know, as you're aware, you'd like to have kind of, in some cases, almost turnkey processes for your users so that you can solve their needs in a better fashion, in a quicker fashion. But again, the typical project might be something that's a 3 to 6 month, and we get them in and out. We've done some recent studies for a couple of these ink companies that were comprehensive for a short time. And so, you know, so those are okay for the short periods, but for us, you know, I think having, you know, at least a relationship that's pretty extensive for like a year is suited best for both the facilities and the staff, and you know, bringing on staffing as well. That's a challenge. So I don't know if I answered your question, but yeah, we see them at all levels. We don't see anything as big as the first one that we had that was more a consortia based project that Jim Watkins brought in, and we just continued to expand on that for over 2 years at that point. So and I'm not convinced those are the best. So sometimes it just gets complicated and there's a lot going on, and then as other users come in, you're not always giving them the attention that they need. That's another challenge that we have.
Yeah, I think that answers the question. I always like the strategy of, you know, just start small, try it out. And then, I mean, a lot of our customers have started one thing and then sort of blossom into using all the different tools. So that's great.
Yeah, and we're getting some of that now, where somebody comes in, they kick the tires on a couple of things, they're pretty happy, and then they come back. So that is a nice interaction. And as you probably understand, everybody's different. Some partners are awesome, and some are. I'm not gonna say anything bad, but I mean it's the time you spend trying to manage and work with them is some people are really easy and straightforward, and others takes a lot of time and effort.
Okay, it looks like there's no more questions. So thank you, Jeff, so much for that talk. And thank you all for attending today's seminar. Our next seminar is scheduled for Tuesday, October 19th, which we will have Dr. Kevin Dagbay from Scholar Rock, who is also a UMass alum, tell us about his work with Steve Iles and the Mass Spec Core facility. Hope to see you there. Bye, everyone.
All right, bye-bye.